All right, good morning, everyone. So, welcome to our last day of class. So tomorrow will be exam number 5, and then Wednesday next week will be our final exam. I'll post some things about those, but the exam tomorrow will work the same way as the final exam, which will work the same way as the lab exam, where I'm going to have you guys sign into Zoom, and then I'll stare at you intently the entire time that you're taking the exam. So, and awkwardly, it'll be great. Okay. So, but I'll send out more information about that later. So, having said that, let's finish off this wonderful chapter. So good. So, next thing we want to look at is combinations of lenses and mirrors. So, any type of combination that you can think of. So, basically, any useful type of optical instruments is pretty much made from combinations of lenses and mirrors. So for example, microscopes, telescopes, all those fun things are made out of combinations of these objects. So for example, show you, these are 2 different types of telescopes. This one is what's called a reflecting telescope. So basically the eyepiece is down here. So this is the side which points at whatever it is that you're looking at. So for example, if you're looking at the star or the moon or something like that, the light comes in here, hits this back primary mirror back here, gets reflected then to a secondary mirror, which then gets reflected through the eyepiece, which then goes into your eye. So this is what's called a reflecting telescope. So here, this is a combination of actually 2 mirrors and a lens. And this is actually what's called a refracting telescope. So this is one that doesn't use any mirrors. So same thing here, you would point this at whatever object that you're looking at. And then the light comes in, but here it's actually just a combination of lenses. So here I would actually have 2 different types of lenses, or actually typically what you're going to have are 2 diverging lenses. So you'd have 1 diverging lens here and 1 diverging lens here. And the reason you have diverging lenses is because the light's coming in at an angle. So by the time it comes through here, you want it to go pretty much straight. So you want it to then come in a straight line and then come into the second diverging lens, where it then is going to diverge outward. But again, it just depends on the type that you're using. Sometimes it could use 2 converging lenses, could use 2 diverging lenses, or a combination thereof. But again, typically, optical instruments are created from combinations of lenses or lenses and mirrors. So here, let's look at an example and let's see how to actually consider a problem which is made out of a combination of, in this case, 2 lenses. Now, even if this was a lens and a mirror, it would work pretty much identically the same way. So the first things first is let's talk about how we actually draw a ray diagram. So the way we draw the ray diagram is exactly the same way we're going to do the math for it. Is we're going to consider only 1 lens or 1 optical object at a time, which pretty much means that here, I'm going to draw my ray diagram only for lens A, ignoring the fact that lens B even exists. Then, after I draw my ray diagram for lens A, what will happen then is that the image, which is created by lens A, will then become the object for lens B, and then I'm going to draw my ray diagram for lens B, ignoring the fact that lens A even exists, okay? So after we do that, everything else pretty much works the same. So we're going to use the same rays that we did before. So I'm going to draw ray 1. So again, ray 1 is going to be the ray which again goes parallel to the principal, hits the center of the lens, and then refracts down through the focal point of A. So this is then ray number 1. Ray number 2, again, is going to be the one which goes through the close focal point, because this is a converging lens. This guy's going to pass through here, hit the center of the lens, and then it's going to go parallel to the principal. So this is now ray number 2. So as we talked about yesterday, where these 2 lines converge, this is the location of my image, okay? So if I put some nomenclature on here, the distance then from the center of the lens to where the object is, I'm going to call that S of A. So that is the object distance from lens A. F of A then is the focal length of FA, and now we can call this from the center of the lens to the location of the image, then image distance A. Now, these 2 lenses are separated by a distance of D, so what happens now is, since I've already drawn the ray diagram for lens A, this image from lens A now becomes the object for lens B. So now what's going to happen is that this distance here is now going to be my object distance for lens B. So this is going to be SB. So from here, we're just going to do the same thing. So I'm simply going to draw my ray diagram. So I'm going to draw ray number 1. So that's going to be the ray that goes parallel again to the principal. It's the center of the lens and then gets refracted through the far side focal length or focal point. So that's ray number 1. Ray number 2, what color haven't I used yet? I haven't used. I guess I'll do it in green. Again, this one's going to go through the near side focal point, hit the center of the lens, and then gets passed through parallel to the principal axis. So this is ray number 2. And then finally, where this two cross each other, this is then the location of the final image. In this case, if I have only 2 optical instruments. So this is then my ray diagram. So good. So then this distance here from the center of the lens then to where the object is created, this would then be object distance B, which is going to be equal to our final location or our final image distance. And then again, this distance from the center of the lens to the focal point is then focal length B. Okay. So the question is, how do we then mathematically do this? So this is how we draw the ray diagram. But how do we mathematically do it? Well, the way we mathematically do it is just we're going to apply the Thinlits equation twice. So I'm going to first apply the Thinlits equation over here. So for example, let's say if I'm looking for the image distance from the first lens, then this is going to be equal to the object distance of the first lens times the focal length of the first lens divided by the object distance minus the focal length. This just comes from what we talked about yesterday in those example problems. So the next question is, well, how do I find now the object distance for B? Well, notice that D here, which is the distance between the 2 lenses, is the same thing as adding the image distance from A plus the object distance from B. So here, by looking at my geometrical representation, I can say, well, D is the same thing as SA prime plus SB, which means SB then, which is the new object distance, is then equal to the distance between the 2 lenses minus then the image distance. Now, this is going to be true for any type of lenses I drew here. So even though I drew this for a combination of 2 converging lenses, this is always going to be true regardless of the type of lenses that I'm using. So even if my image was created out here, it would still be the same expression. Okay? Then from here, now to find the final image distance, well, the image distance then, SB prime, would then just be equal to SB times FB divided by SB minus FB. Okay? So here, the only thing that connects the 2 of them together then is the distance between the 2. So once I find the image distance for the first lens, I then subtract that from the distance between the 2 lenses, and then that's going to give me my new object distance. From that object distance, I can now find the new image distance. So this is how we handle 2 then, or a combination of lenses. If I had a third lens, I would just do it again. So if I had some third lens out here, so let's pretend I had a third lens for now. So if I put a third lens out here, where this one, say, might be separated by another distance of D2, I would just do the same thing. So then SC, for example, then would be equal to D2 minus then SB prime. And then I would do the same thing down here. Right? So I would do this for no matter how many different lenses that I had. Now, the magnification though, so what's the magnification? So the total magnification then is going to be the product of all the magnifications. So let's talk about the magnification. So M total then is going to be equal to the product then of, in this case, the magnification from lens A times the magnification from lens B, which means that this is going to be equal to the negative SA prime divided by SA times the negative SB prime divided by SB. Right? So this is the negative of the image distance from the first lens divided by the object distance for the first lens, and then times that from the second lens. So then this is equal to simply SA prime SB prime divided by SA SB. So the total magnification then is simply equal to the product of the total magnifications. So if I had 3 lenses, in that case, then my total magnification then would just be equal to, again, the product of all 3 of those. And so I would just multiply all 3 of these guys together. And with a 4th lens, then it would be MD and then et cetera. So in mathematical terms, we would write this way. Anybody familiar with the uppercase pi with an I underneath of it? guys seen that before? No? Okay. This is the same thing as this, right? This is an infinite sum. This is an infinite product. Just a fancy way of saying I'm going to multiply all these things together. So that's it. So this is how we handle these. Now, again, if I go back, be a little bit careful here. These equations that I wrote here are not general. These ones are only true for converging lenses or convex or concave mirrors. So these are only true for converging lenses / concave mirrors. If I don't have one of those, then this expression doesn't work anymore. But this one is general for all cases. So this is general. So good. So let's use this and let's do an example. So, let me find my example here. There it is. So this says I have two converging lenses, A and B, with focal lengths FA, which is 20 centimeters, FB, which is 25 centimeters, are placed 80 centimeters apart. An object is placed 60 meters in front of lens A. Determine the position and the magnification of the final image formed, proper English, there we go, by the combination of the two lenses. Great. So the nice thing about this is I actually did all the work for us. The only thing we have to do now is plug in all of our numbers. So let's do all that. So let's go ahead and do that. So here we're told that what? D, which is the distance between the two, is equal to what? 80 centimeters. We're told that the object distance is 60 centimeters. We're told that FA is equal to, what was it, 20? 20, and then FB is 25. Good. So this is then 20 centimeters, and then FB is then 25 centimeters. Good. So from here, we can then find SA prime. So SA prime then is going to be equal to, again, SA times FA divided by SA minus FA. So this is going to be equal to, where am I? So this is going to be 20 times 60 divided by 40, all with units of centimeters. Right? Good. So what this gives me a 2, so this should then be equal to what? 30 centimeters, right? Good. So from here, I can now find my new object distance. So SB then is going to be equal to FB, or sorry, D. There we go. I can do this right. So this is going to be equal then to D minus SA prime. So this is going to be equal to 80 minus 30 units of centimeters, which is then equal to 50 centimeters. So finally from here, we can then find SB prime. SB prime then is going to be equal to SB times then FB divided by SB minus FB. So this is going to be equal to SB, which is 50 times 25 divided by 25, which is then equal to 50 centimeters. Okay, so what this 50 centimeters is telling us is, let's go back to our picture, that this guy is 50 centimeters away from the second mirror, or sorry, the second lens. So this guy is 25 centimeters beyond the second lens. So this is part A. Part B then says, what's the total magnification? Well, we now know the total magnification is equal to SA prime times SB prime divided by SA times SB. So this is going to be equal to 30 times 50 divided by SA, which was what, 60, times SB, where SB was 50. Good. So this one cancels out. This then gives me simply a half. So my total magnification in this case is a half. So if I go back to my picture, all this is saying is that this guy here should be half the size of this guy, which is, again, I didn't actually measure this out, but that's roughly about true in this case. So good. So this is exactly how you would do combinations. And like I said, this works exactly the same way. For example, if I put a mirror here, or sorry, put a lens here followed by a mirror. So this exact scenario would be exactly the same. So in this case, first thing you would do would be draw the ray diagram for lens A, ignoring the fact that the mirror existed. Once you then draw that, the image becomes now the object. That object, then you would draw the ray diagram for him, ignoring the fact that lens A actually existed and only draw it for the mirror. And then again, mathematically, first you would use the Thinlits Equation for lens A, and then use the fact that these guys are separated by some distance of d to then find the new object distance. From there, then you would apply the mirror equation, which is the same as the Thinlits equation for mirror d. And that's it. So that's how we do combinations of lenses. So the very last thing we're going to talk about is what's known as the Lensmaker's Equation. So the Lensmaker Equation tells us how do we deal with things which have different radii of curvature. So what does that mean? So that means, let's say if I had a lens that looks something like this, kind of look like a crescent if I knew how to draw. Looks more like a Pac-Man, but that's fine. Let's say I had something like this, or if I had something which had kind of a small or large radius of curvature on this side, and then a smaller radius of curvature on this side, right? So how do I deal with things like this? Right? So how do we actually determine the focal length for something like this? So what the Lensmaker equation says is the following. So let's call that the left-hand side here is radius 1. So this thing's going to have a pretty big radius. So this is going to be radius 1. And then the other one, the one which is on the right-hand side, then is going to be radius of 2. Right? This one has a smaller radius. Let's call that R2. So what the Lensmaker equation tells us then is how do we actually determine this focal length? So what it says then is that the focal length is determined as 1 over the focal length is equal to the index of refraction of the lens minus 1 times 1 over radius 1 minus 1 over radius 2. Okay. So things to note here. If the radius R1 comes from the right-hand side like I have drawn here, this would be considered a positive radius. If radius R2 comes from the left-hand side like I have drawn here, this would also be considered a positive radius. So meaning that if I look at this scenario here, the one I have drawn on the left, R1 here would still be a positive radius, but R2 is coming from the same side at which R1 is, since it's the lens portion on the right-hand side. So in this case, R2 would actually be negative. Okay. So in this case, this would then be a negative radius where these guys would be positive. Okay. So that's just how we would determine the signs on these particular radii. So it looks like what I have drawn here, these are then positive radii. If it looks anything else, then these guys would be then negative radii. Okay. So for example, if I was looking at a diverging lens, something like this, both of these two radii in this case would be negative. Okay, because the one on the left-hand side, this would then be R1, which is coming from the wrong side, so this would be negative. R2 then would be like this one, so this would be R2, which would also be negative. Okay, so the point of having this guy there is only to find the focal length. Once you find the focal length, the rest of the problem proceeds exactly the same way as usual. So the only thing this would be inserted for would be on like a part A, find the focal length based off of the different radii. And then once you know the focal length, then you just treat it like that particular lens. So for example, if you found the focal length was positive, then that means it has to be a converging lens. So when you draw your ray diagram, just draw a converging lens and then do your ray diagram as usual. If you found the focal length was negative, that means it acts as a diverging lens. So just draw it like a regular diverging lens and then do the ray diagram as usual. So let's do an example. So this one says we have a convex meniscus lens is a convex lens on the left-hand side of the lens and a concave on the right-hand side. Okay. So let's draw what that means. All right, so it says the left-hand side then is convex. Okay, so the left-hand side then is convex, which means it's going to do this. So remember, convex means it points towards you. And the right-hand side, it says concave. Remember, concave just means we're going inside, so this thing is actually doing this. Okay, so this is my concave. So this is my the lens that we're talking about in this case. Where am I? All right. So this is my convex meniscus lens. So this says, if the lens is made out of glass with an index of refraction of 1.5, the radius of curvature of the convex surface is, so that's going to be my R1. So R1 in this case is a positive 22.4. So let's write that down. So here we know R1 is going to be equal to a positive 22.4 centimeters. R2 then, where am I? There I am. So R2, the concave side, is 46.2 centimeters. So in this case, all that means is that this guy is negative, right? So I have a negative 46.2? Yeah, centimeters. Good. And we know this is made out of glass where the index of refraction is 1.5, and that's it. There we go. So good. So from here, what it wants to know is what is the focal length, and then where the image be if the object is 2 meters in front of this particular lens. So good. So let's look at part A first. So part A is we want to know the focal length, so that means we have to use our Lensmaker equation, which says that this is equal to n minus 1 times 1 over radius r1. In this case, I'm going to put a positive sign in here, r2, because I have a negative of a negative. So in this case, I have a negative, but the R2 is negative. So I'm going to put this in with a positive sign and call this the absolute value. So good. So from here, I just want to invert this guy. So I'm going to find a common denominator, which is R1 and R2. So this guy's going to become what? N minus 1 times R1 plus R2 divided by R1, R2. So finally, let's invert, which means that F then is going to be equal to R1 times R2 divided by n minus 1 times R1 plus R2. So this is my focal length. Plug in my numbers. If I did this correctly, this should work out to be about 87 centimeters. Part B then wants to know, okay, so where is our image created? Well, in this case, since our focal length is positive, what that means then is this thing acts just like a converging lens. So for part B, let's go ahead and draw a ray diagram. So here, even though I have that complicated looking lens, I'm simply going to draw a converging lens. That's it. So we know the focal point is here. Focal point is here. It's about 87 centimeters, and our object is what? Roughly twice the distance of that. So our object is going to be somewhere out here. So let's go ahead and draw a ray diagram. So again, draw ray number 1. It's going to go parallel to the principal, to the center of the lens, get refracted down through the focal point. And then ray number 2, again, goes through the focal point on the near side, hits the center of the lens, gets refracted parallel to the principal. Where these two guys meet up with each other, again, that is the location of the image. So what this says then is that our image should be real. It should be inverted, which means that the magnification should be negative, and the image distance should be somewhere bigger than 87 centimeters. Right? It should be outside of the focal length. So okay, so let's plug that in. So now we have that the image distance, S prime, then is equal to S times the focal length divided by S minus F. So this is now going to be equal to 2 meters times 0.87 meters divided by 2 minus 0.87. Plug in our numbers. What we find in this case then is this works out to be about 1.54 centimeters. And that's it. So as I said, so with the Lensmaker equation, the only thing it wants you to do then is knowing the different radii and the index refraction is to first find the focal length. Once you know that focal length is not going to change. So now just treat it like the type of lens that it is, which is going to be either a converging lens or a diverging lens, and then just proceed through the problem the way that you usually would, knowing that it's a converging lens or diverging lens with a particular focal length. And that's it. We doing okay?
For radius 2, you put a negative in front of it, but you don't use the negative at all, do you?
Well, I didn't because, well, technically I did, because remember here, this should be a negative sign. So
Oh,
I
okay.
actually, when I put the magnitude on here, I use the fact that this was negative to make this guy a positive. Because if I go back to what I wrote down before, this should be a negative, but since R2 is negative, I have a negative, which gives me a positive.
Okay, thank you.
You're welcome. Does that make sense?
Yes.
Good. Okay. Nobody's doing okay? Not too bad. All right. Well, that's it. We're done. Everything is done. So from here, we can now start doing a review for tomorrow's exam. So good. So let's talk about, what's that?
Real quick, so for the diverging lens, is that the only one that doesn't go through to make your ray from the back?
Correct. So when they do the diverging lens, so since the focal length is technically on the back side, in that case, so ray number one would still do this and then diverge away from the front one. But then when I'm drawing ray number two would try to go through, this side on here. And by the time it hits the center of the lens, it then goes in this direction. Exactly. Yeah.
Okay, thank you.
So it's just opposite of what you would do for the converging lens. So instead of the near side, you go to the far side. That's right. Everything okay? All right. So good. So I believe the first chapter was chapter 31. Is that right? I don't quite remember. I'm getting too old. Okay, anyways. But this had to do with Maxwell's equations, and more importantly, what care for us is the Maxwell-Ampere's law. So Maxwell's Ampere's law. So this was the big important thing for us. So Maxwell's and Ampere's law says that the closed loop integral of the magnetic field dotted by the differential length is then equal to mu naught times the enclosed current plus the displacement current, where the displacement current is equal to epsilon naught times the time rate of change of the electric flux, where the electric flux is equal to the integral of E dot dA. So not the closed loop integral or the closed surface integral, but just the integral of E dot dA. Now for us, for the exam purposes anyways, we're not going to care about this part, the I enclosed. That was, we already did that before with Ampere's law. That was exam 4. So what we're really going to concentrate on is just the displacement current, which means there's going to have to be something in here which is time dependent, which for us will actually be the electric field. So the electric field itself will be time dependent, not the area. So our area is actually going to be fixed. Good. So from here, we also looked at the pointing vector. So we said that the pointing vector was the electric field crossed by the magnetic field divided by mu naught is then equal to S, where S is what's called the pointing vector. So remember, the pointing vector tells us the direction of propagation, and it also tells us the intensity. So if I took the magnitude of the pointing vector, then this is equal to the RMS electric field times the RMS magnetic field, all divided by mu naught, where the RMS's are equal to the amplitudes divided by the square root of 2. Okay. And we also know, that the magnetic field is related to the electric field by the speed of light. So the speed of light is equal to the ratio of the electric field to the magnetic field. So I'm going to write this as the amplitudes. Good. From here, we can then find what's known as the radiative pressure. So the radiative pressure then is equal to A times the intensity divided by the speed of light, where A is typically somewhere between 1 and 2, where 1 is when it is totally absorbing, and 2 is when it is completely reflecting. So this is a perfect reflector, and this is a perfect absorber. So for our exam, it'll basically be either 1 or 2. So it's not going to be anywhere in between. It would just be one of those two. So here you just have to know, if I tell you that it strikes a surface which is reflecting, you'd have to know to use 2 in this case. Okay? Or if I tell you it hits a surface which is absorbing, in that case, then you would just have to use 1. Okay? From here, you can then get a radiative force. So the radiative force then is equal to the area times the radiative pressure. Okay. Now, in this case, this area is the area which is being struck by the light. Okay. So not just any old area, but the area specifically by hitting the light. Okay. Or the light is hitting it, I should probably say. What else did we do in this chapter? We also talked about polarization, right? So polarization. Good. So for polarization, what we saw was if we have unpolarized light going through a polarizer, then automatically the intensity is reduced by a half. So this is equal to 1/2 of the initial intensity of the light. Afterward, if I have polarized lights going through a polarizer, in that case, the intensity then is equal to the initial intensity times cosine squared of the angle between the original polarization and the polarizer. So all that means then is what? So if this is my axes, so let's say this is X and Y, and my electric field is, I don't know, say initially aligned along here. So this is my initial polarization axis. And I send that then through a polarizer. So here's my polarizer. Let's put a coordinate system on here as well. So X and Y, and my polarizer is aligned, I don't know, so that it allows the light coming through in this direction. Then basically if I superimpose these two things on top of each other, then the angle between the two, in this case, would be this total angle here. So this would be the angle between the two. Okay. So here, this is the angle specifically between the original axis of polarization and the axis of the polarizer. So that's this guy. This is what's called Malice's law. Cool. We do anything else in this chapter? I don't think so. I think that was about it. Okay, so good. Next chapter was chapter 33. So chapter 33 here is where we talked about dispersion of light and diffraction of light. So we did a few things here. So the first thing we did was the Young's double slit experiments. So for the Young's double slits, what we said was that the path length difference was basically equal to the distance between the slits times sine of the angle between the two. And then that was equal to n times lambda, or n plus 1/2 times lambda. And this was for constructive interference, i.e. the bright spots. And then this was, and technically this depends on n as well, and this was for destructive interference, which was the dark spots. What else did we do in here? So we also did, I'm going to skip the thin lenses. So we did thin film, sorry. Thin film interference. So here we said that the path length difference, delta D, was approximately equal to simply twice the thickness of the thin film, which was then equal to n times lambda, or n plus 1/2 times lambda. And this is lambda 2, where this is lambda in the second medium. Or this was equal to n plus 1/2 times lambda 2, and then n lambda 2. Okay. So the first one occurs when I have either 0 or 2 phase shifts. And then the second one occurs when I have 1 phase shift. And remember lambda 2 here, write that over here. So lambda 2 is then equal to the wavelength in the first medium, or whatever the wavelength is, divided by the index of refraction, n2, of the second medium. So what constitutes a phase shift? Well, a phase shift happens when we go from a high index of refraction to a low index of refraction. Or sorry, we go from a low index of refraction to a high index of refraction. Sorry, I had that backwards. So a phase shift occurs when we go from a low index refraction to a high index refraction. Okay. So again, here you have to look at what's happening on each one of these different boundaries. So you're gonna have an N1 here, an N2 here, and an N3 here. So basically you just have to look at the size of N1 relative to N2 and then N2 relative to N3. And that'll tell you which one has a phase shift and which one doesn't. So again, here, if I go from air to water, I end up with a phase shift. If I go from water to glass, then I end up with a phase shift. Because we know water has 1.33, glass has 1.5, so I'd go from a low to a high and a low to a high, so I would have 2 phase shifts, which would put me back in this scenario. So good. So there's that. What else did we do? We also did the law of reflections. So the law of reflection says that the angle of incidence is equal to the angle of reflections. So here, if I have an incoming ray striking the boundary at an angle of theta incidence relative to the normal, then this guy gets reflected off at an angle of theta reflection, where theta reflection is exactly the same thing as the thing of incidence. Index refractions, I should probably talk about that as well. Index of refraction. So index of refraction is defined as the speed of light divided by the speed at which it's moving inside of the medium. So that's my index of refraction. And then from here, this means the speed at which it's moving inside of the medium is the speed of light divided by the index of refraction. So from here, index of refraction must always be greater than or equal to 1. Money's okay. What else did we do? We did Snell's law. So Snell's law says that, again, if I have a boundary, so here's my boundary. Again, if I have an incoming light, which then strikes the boundary, there we go. So this comes in at an angle that's, say, theta 1, and then gets transmitted or refracted into the second medium at a different angle, theta 2, which then depends on the index of refraction. So this is theta 2. So Snell's law says that n1 times sine of theta 1 is then equal to n2 times sine of theta 2. Let's see. Are we doing anything else in this chapter? Talk about that in films. No, I think that's it. All right. So that's chapter 33. Finally, chapter 34, which is the one we just finished up here. So chapter 34, we have the mirror equation. So the mirror equation says that 1 over the object distance plus 1 over the image distance is equal to 1 over the focal length. And the magnification is that what? M is equal to h prime divided by h, which is equal to negative s prime divided by s. Now notice that the mirror equation actually works for both plane mirrors and spherical mirrors. So the only difference is if I want to get a plane mirror out of this, a plane mirror occurs when the radius of curvature is equal to infinity, which means that the focal length is also equal to infinity, which means that I have 1 over infinity, which is 0, which then automatically tells me that s is equal to negative s prime. So inside of here is actually the plane mirror as well. So we don't need anything separate then for the plane mirror. And because these two are just equal to each other, it means magnification is always equal to 1. So not too bad. Good, so that was that. We also then have the Thinlits equation, which is exactly the same thing. And we have the magnification, which again is the same thing. Life is great. And then finally, we have the Lensmaker equation, which now we know is 1 over the focal length is equal to the index of refraction minus 1 times 1 over R1 minus 1 over R2. So that's it. This whole entire chapter was 3 equations. Not too bad. Not too bad. So that's it. So good. So let's talk about what's going to be on the exam. So first things first, one long problem will definitely be this stuff. So all of this is going to be one long problem. So inside of here, you'll be responsible also to draw the ray diagrams. So the ray diagrams. So expect in here also a combination of lenses or lenses and mirrors. Combination of lenses / mirrors. Okay. So that's one long problem. Typically, this is everybody's favorite problem because this is nice and easy. So, good. So next long problem is definitely going to involve this. So I mentioned this when we did it, but this is going to be one long problem. So basically here, you're going to be looking for things like you're going to have a parallel plate capacitor, which I'm typically going to do a spherical parallel plate capacitor, which has some given area, so you don't have to worry about that. The only thing that's going to be changing on the inside is the electric field. So basically from there, you'll have to find a magnetic field, which is induced inside the plates and outside the plates, but only between the plates. One other thing that will be useful here is from exam number 3, and the fact that the electric field is related to the potential by the distance. So this will be useful for this problem. We did an example like this in class, so go ahead and take a look at that example. So here, basically what will happen is as long as the electric field is only time dependent and not spatially dependent, then the flux will simply be equal to the electric field times the area, which means you won't have to do an integral, but you will have to do a derivative with respect to time. So, but not too bad. Be a nice, easy derivative. Okay. And then the last long problem, if I remember correctly, will basically involve this stuff. So basically radiation pressure, radiation force. So we did an example like this in class. But one thing that'll be useful here is, remember, intensity from a point source is given as the power divided by the surface area. So this is going to be equal to the power divided by 4 pi r squared. Okay. So, and again, this is the intensity from a point source. So those are the 3 long problems. So again, one of them is, this one's basically going to be going back to 205 for the most part. So looking at forces and some of the forces and all that kind of good stuff. This one, as I said, we did a couple examples like this in class, but definitely look at those. And then the last one will be, again, combinations of lenses and all this kind of good stuff. So magnifications and et cetera. Other things to talk about. So what are the short ones going to be? So one short problem. What color should I use? Because I'll use blue. So one short problem is going to be this stuff. So polarization. So it's going to be a short answer, quick calculation problem. Another one is going to involve this stuff. So the RMS values and pointing vectors and intensities and all that kind of good stuff. So this will be another short answer, quick calculation problem. And what's the last one? Oh, yeah. So this stuff here, Snell's law. So this will be a short answer, quick calculation problem. Good. Good. Sorry, I had to remember that. Which means that the extra credit will be thin films. Unfortunately, Young's double slit didn't make the cut this time. Sorry about it. Sorry, Young. Young's didn't make it. Not everybody can make the team. It's fine. Okay, so any questions on the exam? This is usually kind of a straightforward exam. The hardest one will, of course, be this one, but we did enough examples of it. It'll follow similar to those examples, just have a completely different time dependence. So, but otherwise, just make yourself comfortable with those examples and you should be fine. Everything else should be pretty straightforward. There's no real tricks anywhere. So, so good. Any questions on any of those things?
In the Lensmaker's equation, how do you determine if your radius is positive or negative?
Oh, so let's go back. So basically it comes from the picture. So it has to look like this. So if it doesn't look like this, then they're negative. So basically radius 2 is going to be the one on the right-hand side. So it has to bulge out towards the right-hand side. And radius number 1 has to bulge out from the left-hand side. So if it doesn't look like this, then it just has to be negative. Is that okay?
Yeah, thank you.
You're welcome. So last couple things I guess I'll talk about are, there are 3 more group assignments. Get some more extra credit points. One is similar to the one I gave you yesterday, but this one deals with lenses. So this one again is just fill out this chart. So again, I'm telling you the focal length, I'm telling you the the object distance. You then have to find the type of lens, which in this case is a converging lens because this is positive. Find the image distance, magnification, real, virtual, upright, or inverted. This is then a Lensmaker Equation question. So this one you have, you're telling where it is. It's a plano convex, which means the radius of curvature on one side is infinite. On the other side, it is then 13. So you also know the index of refraction is 1.7. So find the focal length, and then from there find the location. Is it virtual or upright? And then finally, the last one is a combination of converging lenses, where I tell you the distances here, tell you the focal length for each of them. So I want you to draw a ray body diagram, find the final position, and then the final size. Even though I don't think I told you the actual size of the object, so just make this, what is the magnification? So the final magnification, not the final size. Okay. So that's it. So I think that gives us 8 group assignments total going into the last exam here. So not too bad. Not too bad. And those have been on Blackboard, I think, for a few days now. If they're not there, just let me know. And I'm currently uploading the videos from Monday and Wednesday, so those will be up today. So I actually just finished the one from Monday, so that one is up there. So those will be up there in a little while, so in case you want to look at those, if you forgot something, want to go through those again, those will be up on Blackboard on YouTube. So any questions? Like I said, tomorrow's exam is usually a nice, easy one. I'll put out more information about it, but I'm going to have you guys do the same thing that we did for the lab final. So again, you guys are going to have to sign on to Zoom like you are now. Just make sure you turn on your cameras, turn off the microphones, and then just like you did with the lab finals, if you have any questions, just send me a message on the private. I'll be here probably grading all my backup quantum mechanics homework that I have not graded for a while because I'm a bad teacher. Anyways, so yeah, so any questions about any of this stuff?
Is it going to be like take a picture of your...
Yes, exactly, yeah. So what'll happen is there's already a folder set up on Blackboard. So pretty much once you sign on, then just go to Blackboard, because I think the exam will show up on Blackboard at about 8:50, I think, is when it's going to show up there. So it'll show up automatically onto Blackboard. So pretty much you'll have from 8:55 to 9, 9:55 to complete it. And same thing, yeah. So you just take pictures of the exam and then just upload those onto the different submission links. So all those submission links are already set up on there as well. So all the ones for the group assignments, for the outside extra credits, for short answers, and for the questions, and for the on-exam extra credit as well. So all those are already up on there. So yeah.
Okay, thank you.
You're welcome. So yeah, so just take pictures and upload those, and you'll be fine.
And you said 9:55 is a cutoff, right?
Well, that's when it'll be say it's due. Yes, yes,
Okay.
that's right. Yeah. So 9:55. So I'll give you a. Well, actually, that's when you should stop working on an exam, but I think I put it so it's due technically at 10:30 to give you time to take pictures and upload it. So yeah. So yeah. So technically, you get to work on it until about 10 or 9:55, and then from there you get an extra 35 minutes to take pictures and upload and do all that good stuff.
Is it going to be through the same Zoom link, or is it going to be posted to Blackboard?
Oh, the same one that you're using right now. Yeah.
Okay.
Yeah. So that's already set up for tomorrow. Yeah. Yeah. And then I'll have to set up a new one for the final next week. Everybody's okay? Not too bad. So this is another good one to make up some points on if you're in need of some points. But other than that, this is our last class together. I'm gonna tear up and cry, but it's fine. Okay. Everybody's okay? So I'll see everybody's smiling faces or confused looking faces tomorrow, whichever happens to be while you're taking the exam. And then otherwise, I will see you on Wednesday for the same thing. And yeah, and then that'll be it. And after that, have a good break, everybody. So, all right. See you guys tomorrow. Bye.